today's class we are going to start with cyclic coordinate and conservation of linear momentum. But the topic is a bit long, but anyway we'll start. So the first is cyclic coordinate. Cyclic coordinates are also called ignorable coordinates. This is actually the last topic of your first unit, but then there is a smooth transition to the second unit because you use cyclic coordinate, use the idea of conservation of linear momentum, where we use the concept of generalized momentum also to understand Lagrangian. We actually derive a relation for Lagrangian using that. Okay, so we need to have a clear picture of this. So cyclic coordinate is also called ignorable coordinate, and why it's called ignorable, because if there is a coordinate which is cyclic in nature, we kind of don't involve it in the equation of motion, and that's why it is called an ignorable coordinate. Okay, so please note this. Your exam, the question might be what is a cyclic or an ignorable coordinate. Okay, so before I go to this, okay, and you can see my handwriting here. Okay, I hope you can understand it, but anyway I'll dictate it, not a big deal. And uh, what happens here is that whenever we are talking about something like Lagrangian, what exactly does Lagrangian mean? Because I've used the term Lagrangian, if I don't explain it to you, I think it will be a bit confusing. So let me just explain a bit of it, okay? As we go along, we are going to understand it better. So what happens is whenever you write down Lagrangian, it's actually nothing but kinetic energy minus potential energy, okay? So from now onwards, I'm going to refer to T as kinetic energy and V is potential energy, capital V, okay? And I think V as a potential energy has been a very common notation, but kinetic energy sometimes people do use K and Ke and so on. But in this terminology, classical mechanics, we are going to use T as the kinetic energy. Okay? So don't get confused. So whenever you can actually write down an equation which has got kinetic energy and potential energy form, that means you are describing the motion of the system, right? You have information about the motion of the system, because let's say you are considering a simple pendulum, or let's say you are considering the swing, okay, or you are saying something rolling down a inclined plane, okay, and so on. So whenever you consider these kind of bodies, okay, free bodies, what happens is they do have some equation of motion involved with them. Let's say for example a pendulum. I think pendulum is something which we all are aware of, and we know that we actually can make it swing, let's say by an angle theta. In this case, theta will act as a generalized coordinate, and it can go on this side also. Okay, as soon as it reaches the extreme end, it stops momentarily. So that means the potential energy will become zero because the velocity is zero. But then at this particular point, the kinetic energy is the potential energy is maximum, right? Potential energy is maximum, and this is your kinetic energy, which will be zero, no kinetic energy. Okay, so what does it mean? That here potential energy is maximum, and if you consider this particular point, kinetic energy is maximum, kinetic energy is maximum. So you know that if you consider these kind of things, that if you go from here to here, it's basically a mixture of kinetic energy plus potential energy. Anywhere you consider, let's say this particular point, you will have both kinetic energy as well as potential energy. Okay, so that's why whenever you write down the equation of this pendulum in terms of kinetic energy and potential energy, you are describing the motion of the entire system. Okay, and this is what exactly Lagrangian does. This is what exactly Lagrangian does. But then if you are considering a very complicated system, let's say not the pendulum, what happens is there are more and more coordinates there, which makes it more complicated. And that's why we come back to classical mechanics, try to understand generalized coordinate, implement generalized coordinate to simplify the Lagrangian and find out an equation of motion. Okay, so this is what is Lagrangian is all about. Okay, so don't get confused. It was Lagrangian who has given this concept and idea, okay, long before quantum mechanics actually was into the picture, and this is still valid, and so we consider it to be very appropriate for this particular syllabus. Okay, so what happens is when we take Lagrangian, it's basically a function of generalized coordinate. Okay, so it is function of generalized coordinate Qj. So I think we already know about generalized coordinate now. We can take in this case we can say theta is the generalized coordinate and so on. Okay, so different angles, it might be a measurement of any length, that might also be a generalized coordinate because position vector is there. Okay, try to understand. Okay, that's very important. And then generalized velocity. So if you have theta and you say it's the generalized coordinate, how can you find out the generalized velocity? Simple, del theta del t, right? So you just differentiate it with respect to time, and then you get the generalized velocity. So you have got generalized coordinate, you have got generalized velocity, and you have got time. Okay. So when you write down Lagrangian, okay, when you write down a Lagrangian, it is basically a function of generalized coordinate, generalized velocity. Please don't miss out the dot. Never miss out the dot. Okay, very important. And then time. So this is what is Lagrangian is all about. This is just a function. Okay. And then you might tell me why it's a generalized coordinate, because you know potential energy is mgh, so height, right? So in general, height is basically nothing but a generalized coordinate, right? You can consider this to be a part of the equation of motion, which is nothing but a measurement of length, okay, some length. And then qj dot, that means you are considering velocity in kinetic energy, half mv square, so that means that is there, okay. And then of course velocity is time dependent, so t will be there. But let me tell you very clearly that it doesn't mean always that there will be a time coordinate. If there is no time coordinate, that coordinate is called ignorable coordinate, okay. So that is what is the definition of ignorable coordinate is all about. It's a very simple idea. The term might seem a bit high tech, but it's not, okay. If L does not contain a coordinate qk, so whenever I write down the equation of motion, now this is a very simple case. I'm just considering the motion along the x-axis, okay. The vectors and all, we can actually find out the y-axis motion and so on. So it will be maximum x and y. But let's say I want to consider z-axis also, or as you will learn in your statistical mechanics, there can be n dimensions to a system, okay, at least in the imaginative frame. So if there are n dimensions, some of the dimension you might not consider, okay, and depending on that, some of the coordinate might not be needed. So in this particular case, if z coordinate is not needed, that z is nothing but the ignorable coordinate, okay. So in general, if I give a very general statement, if L does not contain a coordinate qk, very important, okay, and remember the term does not, okay, then this differentiation of qk with respect to the Lagrangian will be 0. It's quite obvious because Lagrangian is a function of qj dot nt, okay, and then and let's say there is another coordinate qk, but the Lagrangian does not depend on that. That will be 0. So this is called a cyclic or the ignorable coordinate, okay. Very trivial, okay. Try to understand this. This is very trivial, but the thing is, when in exam you are asking, you have to write it down in this way, in a technical sense, okay. Don't make just your own sentences. Just try to put this differentiation thing, okay, so that it becomes a bit simpler, okay. So this is your cyclic or ignorable coordinate. Very important. We are going to use it again and again, okay. So what happens is, I think generalized coordinate I already discussed. I don't really need to discuss this. So theta can represent a point on the circle instead of x and y. I think we have already seen this factor. Because if we basically consider this, okay, I think we remember, all of us remember this. This is a big problem here. Okay, so what happens here is this, that when you basically take this, okay, and then this is x and y, and then this is theta, right? Represent this x and y in terms of theta, right? So this is something which you already seen, and theta is called the generalized coordinate. So I've just reiterated that so that you don't forget things. Okay, so next, based on this generalized coordinate, we are going to find out something which we call as the canonical momentum. Now, for your entrance exams, if you're going for your NET or GATE exams, what they do is they do play some kind of trick. Okay, they will change the term. They will give you a different term altogether, and you'll get confused. You might think that, okay, I have not read this. So whenever I am teaching you something, it doesn't mean that's the only term used for it. Sometimes I might miss some points. Okay, and I might not ask that in your exam, but then it's your job that you find out something additional about it. But I'll try my level best that I explain all the terms, whatever the terms are used basically for a particular definition. So when we talk about something like momentum, it can be called as generalized momentum, in this case, conjugate momentum, or a canonical momentum. Okay, so please remember, all these actually means the same. So if someone tells you generalized momentum, it's the same as conjugate momentum or canonical momentum. Okay, please make a note of that. And if you consider a system of mass points acted upon by forces derived from potential dependent on position only, potential dependent on position only. So if you consider a system, we basically system, and we say that there are a number of mass points. So if you consider, let's say, a box, okay, and you have got a number of mass points here, okay, something like this, okay, and it is being acted upon by a force. So you know that force basically is nothing but a potential dependent factor, okay. It is basically dependent on the potential, okay. I think all of us know this, okay. It is dependent on the potential, because when we talk about work done is nothing but force into displacement, okay. And work done, potential energy is nothing but can be converted to the work done, okay. So you know that force and potential are more or less related. So you also know that it depends on the potential, depends on position. If you remember your electrostatics, gravitational field, wherever you go, if you look into the potential and force, there is a major difference. The potential is inversely proportional to the distance, but when we talk about the force, okay, acting between two bodies, let's say in a gravitational field, it is inversely proportional to r square, okay. So please don't get confused, these concepts are actually very important, okay. So let's try to find out the equation of motion of Lagrangian. So this equation we are going to derive, okay. This equation we are going to derive, but probably I can just write it down by the side here, that whatever I have written is actually, it's not very clear, it seems. So this is actually the equation of motion of a Lagrangian, okay. So d dt of del L del q j dot minus del L del q j, okay, is equal to 0. So this is something there, which is the generalized velocity, okay. We already have it. So this is one coordinate and this qj is one coordinate, okay. So this is basically called the Lagrange's equation of motion, okay. So I think I can write this down, okay. I can write this down and just modify this lecture. So this is Lagrange's equation of motion. Okay, this is Lagrange's equation of motion, okay, and this is written as d dt of del L del x dot minus del L del x is equal to 0. So if I'm just writing down it in terms of generalized terms, we just replace that x dot by qj dot and qj, okay. So don't get confused, okay, it's qj dot and qj, and this is called the Lagrange's equation of motion. So you know from your preliminary maths knowledge that whenever you are going to solve for any unknown, okay, and if you are doing going in the chapter of differentiation or integration, depending on how the function is distributed, is it continuous, okay, is it discrete, and so on, you use different operators, okay. So you ddt you can consider as an operator, and then if we can actually know what is the form of Lagrangian, we can actually solve this equation to find out the equation of motion. So this is the equation we are going to use in the later classes for the second unit to derive the equation of motion of a simple pendulum, okay. So if you remember, t is equal to 2 pi root over L by g, all those things we are going to basically use, and we are going to also derive the equation of motion of a simple pendulum. So this comes late, but then we are just understanding cyclic coordinates here, and we are going to use it for this particular concept of generalized momentum. So what can be the question from here is that what is generalized momentum, or derive generalized momentum, okay. So we'll start from Lagrange's equation of motion, and we'll write down this equation, and we will say that qj is cyclic, okay. Please don't get confused here. It's not that qj will always be cyclic. It is considered cyclic here to define generalized momentum, that's all. So the condition is qj is cyclic, and as I told you, in generalized coordinate, if let's say qk is cyclic or ignorable, del L del qk will be 0. So if we consider qj is cyclic, you can say that del L del qj is equal to 0. So that means it does not occur in L, okay. So you can simply write it down as d dt of del L del qj dot is equal to 0. d dt of del L del qj dot is equal to 0, okay. So I think all of us know this, okay. You should not get confused here, that if differentiation of a particular term is 0, that means that particular term is a constant, okay. So I don't want to emphasize on this, but let's just anyway do it, okay. Anyway, let's say I write down something as d dt of a is equal to 0. It straight away says that a will actually have some fixed value, let's say 4, 5, something like this, okay. So that means this a will basically be a constant. It will basically be a constant. So whatever you take ddt of whatever you take, and if this becomes 0, that means that is actually a constant. Okay, so this is why we say that del L del Qj dot is equal to a constant. Okay, not zero, constant. So this is called the generalized momentum. Okay, this term is called the generalized momentum. Okay, so maybe I can just write it here only so that we are all clear here. So this is called the generalized momentum. Okay. Okay, so really need to work on this. Okay, anyway, so this is the generalized momentum. I have it in the next slide, and then a question arises: how? Why I call it as the generalized momentum? Okay, I think this is a very important question, or you need to understand why we call it as momentum. Okay, so in general, we have this very clear idea that whenever we say momentum, it means that we have uh, mass into velocity. So can we find out mass into velocity? Okay, so can we say that here this will be actually nothing but mass into velocity? Okay, or more specifically mass into x dot. Okay, so I really need to do something with this PowerPoint presentation. Actually this is with the PowerPoint system only. It's not a very good annotation tool. Okay, so we have got this P is equal to mx dot. So can I show it this way? Okay, so I can actually, as a matter of fact. So let's try to do this. Okay, try to understand this. It's there on the slide. Let's go line by line. So del L del x dot. Okay, just for ease, I can write down Qj dot also, no problem. Just write down as del L del x dot. Okay, so when we write it down as del L del x dot, we know that L is equal to T minus V. Okay, L is equal to T minus V. So can we just use this here? So L is equal to T minus V. So what you can do is, in place of L, we can replace it with this. Okay, T minus V, as I told you before. We're going to derive the relation, so don't worry. So this will be, if we just separate it out, okay, del T del x1 dot or xi dot minus del V del xi dot. Okay, so one is T, one is V. But then this V is the potential energy. Okay, please don't get confused. Okay, this is the potential energy, right? This is not velocity. If you are writing in a hurry in your exam, sometimes you miss those points. Okay, I don't know if it happens with you or not. It sometimes might happen with me because I'm not in the right frame of mind. Okay, so we have to concentrate whenever we are doing these things. Okay, so don't get confused. This is kinetic energy, this is potential energy, this is actually the velocity factor. But you know, in any general case, this velocity, potential energy does not depend on the velocity. Let's take the simplest example of potential energy that we know, mgh. So this is a function of position. H is a position. Mass and gravitational constant are basically constants, right? So H is a position. So it is function of position only, not of velocity. So that means this term will basically become 0. So that is why this is 0. So if this is 0, this is just del T del xi dot. But then what is T? T is nothing but the kinetic energy. Okay, this T is the kinetic energy. So can we do that? Okay, so let's do del L del xi dot, and let's imagine this is a three-dimensional space. I have not been specified anything, so I'll consider everything here: xi dot square plus yi dot square plus jiz square. So this is nothing but vx square, vy square, vz square, whatever way you want to take it. Okay, so this is half mv square, right? So kinetic energy. So if we take that half m, just keep it outside, and then doesn't depend on I or Z. Okay, and then we are considering only one variable, so you can also remove the summation. Even if you don't remove the summation, it's perfectly fine. Even if you don't do that, just simply write it down in this way. Okay, if you are very confused here, just simply write it down in this way: del L del xi dot is equal to half m, and then xi dot square. Just do it this way. So you can just simply get half. Okay, and then m. Okay, half m, and then xi dot can be written as 2xi dot, right? So that this 2 gets cancelled, we simply get m xi dot. So mxi dot is nothing but momentum, right? So this is the momentum. So what does it mean? It means that yes, this is the momentum. Okay, if you take a differentiation of the generalized velocity with respect to the Lagrangian, you actually get momentum. So see, this is actually basics. It's very basic. Okay, So sometimes I have seen most of the books if you're following, okay, you might follow any book you like, okay, but whatever book you are following, you'll see that sometimes they usually don't mention this, okay. They will straight away say that this part is constant, so that means the generalized momentum is constant, okay. So they won't say that why this is generalized momentum, because it is implied that you know it, okay, because this should be known to you, simple. But then I prefer doing it here, okay. So in your exam also I might ask you some question like show that generalized momentum is constant in case of a cyclic coordinate, okay. But I will ask you an additional question probably, and I'll tell you to explain why del L del Qj dot is actually the generalized momentum, okay. So you have to just do this very simple derivation, so please try to understand it, okay, and don't just write down lines, okay, without understanding. Like you have written here 0 and you don't mention a reason why this is 0, then it kinds of makes a doubt that you are not very clear about the concept, okay. So try to do that, okay, in your exam. I'll be trying to be as lenient as possible, but the thing is, it's important that you understand classical mechanics also. So this is there. So till now I think whatever we have done, you found out that classical mechanics is not that complicated. It's actually very trivial, okay. It's very straightforward, but the thing is when we use a lot of notation and lot of terminology, it brings a wrong sense that it might be very complicated, okay, but it's actually not. It's basically you are analyzing your laws of motion or equations of motion from a different point of view altogether, where you are actually trying to simplify things by involving more and more concepts there, okay, reducing the number of coordinate, and then considering a single function L, which includes both kinetic energy, potential energy, and so on, okay. So this is something which we are doing in classical mechanics, so this is important, okay. And then I'll just add to this generalized momentum. So we can see this, okay. So whatever we have derived, we can see that the x component of the linear momentum associated with the ith particle, okay. So if we want to just generalize the concept, we can say that Pj is equal to del T del Qj dot, which is equal to del L del Qj dot. Again, don't get confused here. If you just forget about this right now, and if you're just going here, you see this del L del Qj dot, okay. So del L del Qj dot is the generalized momentum, but whether you write it down as del L del Qj dot or you write it down as del T del Qj dot, it will remain the same, because del V del Qj dot is anyway 0, okay. So that's why I've said this here, that Pj is equal to del T del Qj dot is equal to del L del Qj dot, okay. So this Pj is actually nothing but not poor joke, okay. Pj means generalized momentum, okay. So it's important that you remember these notations, because this is how it is done, okay. It's not me or you who has made this, it's basically followed. It's a standard notation, so let's just try to follow this, okay. And this is called the generalized momentum. It's a generalized momentum, okay. And we can actually see that this Pj is constant. Why constant? Because I think we have already seen this here. We have it here. So when you write it down in your notebook and see everything at one instant, I think this becomes more clear, okay. Rather than following the slides every time, it becomes a bit difficult. So please make your notes so that you can follow it in a proper way. So this is called the generalized momentum. The question in the exam would be, show that the generalized momentum is constant when Qj is a cyclic coordinate, okay. First question. Second question, show that del L del Qj dot is equal to del T del Qj dot. It represents the momentum. It represents the momentum, okay. I think that is important. So you can always make a note of that question, okay. I think this is important, and this will actually carry around I think 2 marks would be a bit less for this, so I think 3 to 4 marks should be fine. So generalized momentum conjugate to a cyclic coordinate is conserved. So what does it means? The statement, okay. So I can ask you this question also. Show that generalized momentum conjugate to a cyclic coordinate is conserved. Conserve means Pj is constant, as simple as that. Okay? So you have to just show that in that way. So I think this should not be a very complicated thing, okay. So this is clear, okay. One more thing we can look here, that if we this is a different form altogether. ddt of Pj, okay. Pj we know is nothing but del L del Qj dot. So it was del L del Qj dot here, okay. Please write it down everything clearly. so that you are not confused. Okay, del L del, okay, or del L del Qj dot. Okay, so del Qj is equal to 0, and then if we don't consider the cyclic coordinate, okay, if cyclic coordinate, this is 0, but if you don't consider the cyclic coordinate, this Pj dot will be nothing but del L del Qj dot. Okay, we'll need to use it, but then don't include it in your answer. Okay, this is just additional information that we should have. Okay, so this Pj represents the conjugate momentum. I think that is far more important. Okay.